Okay, this lecture is about a couple of topics. First, we're going to talk about some power issues, so power. And the second thing is a concept called impedance flow. I guess power we're going to talk about first. It doesn't really need an introduction. It's we're talking about voltage, we talk about current, power. It's voltage times current, and we'll see how we can look at that going through a transmission line. But the impedance flow is a kind of a strange or interesting concept. And basically, the upshot of impedance flow is if you're looking into a length of transmission line by changing the length of the transmission line depending on the load, where we can basically change the input impedance of the transmission line by just having different distances as seen by the input, meaning that you can use a length of transmission line to get any kind of impedance, which is kind of an interesting concept, and that leads to some other things that are very like key in in RF and TNM microwave transmission line designs, which is Smith charts. So anyway, let's look at the power calculation first. The first thing is um, the question of whoops. So the question is, so we have the positive going voltage and the negative going voltage in a transmission line, and a characteristic impedance. So will there be any power dissipated in T line? Okay, so the answer is, and we're going to look at why we say this. The answer is for a lossless T line, no power is consumed in the T line itself, in the transmission line itself. And eventually, all power is delivered somewhere else, is delivered to the load. Okay. So now let's look at how you calculate power as a factor. So let's say assume we have a um, a voltage that is V0 e to the minus j beta z, and I sub s, these are phasor diagrams, is I sub 0 e to the minus j beta z. So these are the forward going voltages and currents. Of course, this corresponds to, in the non-phasor diagram, this corresponds to T and Z corresponds to V0 cosine omega T minus beta Z, and I sub S corresponds to I0 cosine omega T minus beta Z. So now assume at a constant z plane. So at some point in the transmission line, z plane, we want to figure out the power. So the power is what it's usually written as. So what is power? That's what we're going to try to calculate that point, which is usually written as sort of this bracket v sub s of t times I at s of t. So this is average power in this plane, in this z plane, in the transmission line. Okay, and this stuff in bracket, what this means is it's defined as the integral over a certain period divided by the period integral over that period of whatever is in this bracket. Okay, so these brackets mean this equation, and basically that gives us, this definition gives us the average power over a period of t. Okay, so at the load, so at z equal to 0, v sub s of t I at s of t at z equal to 0 is equal to 1 over t 0 to t v0 I0 cosine squared of omega t is equal to v0 I0 over 2 is equal to the average power. And the definition of RMS voltage is V0 over root 2, and RMS current is I0 over root 2. So average power is basically the RMS voltage and RMS current, so which is V0 I0 over 2. Okay, so that's the power flowing in that section of the transmission line. And then in general, the voltage on a transmission line may be complex. So voltage on T line may be complex, meaning it has an amplitude and a phase, and also the characteristic impedance of the transmission line also may be complex. This is in the case of this would be in the case of a lossy transmission line. The characteristic impedance may be complex, and by complex it means that there is a phase difference between the voltage and the current. So anyway, so the voltage could be V0 plus e to the minus j beta z. I0 plus is all forward going voltage and current, e to the minus j beta z. And Z0 may be complex. And also V0 plus may be complex. May be complex. So in these, and on all these cases, I0 plus is V0 plus over Z sub 0. So average power is V0 plus over 2z times z sub 0. And for a reflected wave, so this is a voltage going in the other direction, the average power is V0 minus squared over 2z sub 0. And then V sub 0 minus is gamma sub L, V0 plus. So average reflected power the average reflected is gamma sub L squared V sub 0 plus squared over 2 sub z sub 0. And then let's define, so define the incident power to be V0 plus squared over 2z sub 0. So average reflected power is gamma sub L squared P incident. And that the square of the reflection coefficient is giving the ratio of the reflected to the incident powers. So what this tells us is that if you have a case of a unmatched transmission line, meaning when gamma sub L is not zero, then basically you get a certain amount of the power coming gets reflected at each end, and then eventually, so you get basically this power bouncing back and forth along the transmission line until all the power is either reflected, sorry, is absorbed either at the source end or um, at the load end. Okay. Okay, so that's basically the power. We'll come back to do some more, look at the power a little bit more later. Now let's look at this concept of impedance flow. Okay, so we looked at the input impedance of a transmission line. So let's say I have a impedance, a transmission line with a characteristic impedance Z sub 0 and load Z sub L. And let's say the length of this transmission line is L. And let's say we're looking at what is the input impedance of this transmission line. So we want to look at what is the input impedance of the transmission line at the point L, away from the load. And going back, if you guys look back a few lectures back, we derived this equation as Z in is Z sub 0, Z sub L plus J, Z sub 0 tangent of beta times L over Z sub 0 plus J, Z sub L tangent of beta times L. So, and then for the case of, Z sub L is infinite, so this is an open circuit case. So the input impedance for an open circuit case is minus j z sub 0 over tangent of beta sub L. Similarly, if z sub L is equal to 0, or short circuit case, so z, the input impedance of the short circuit is plus j z sub 0 tangent of beta L. Okay, so what does this mean? It means if you have a open circuit here and you're looking at this transmission line, basically the input impedance of the transmission line in the case of an open circuit is this equation, and it depends on the length of the transmission line. So depending on how long this transmission line actually is, I get different input impedances. And interestingly enough, well, let's talk about this. Kind of looks sort of capacitive. Okay, it's 1 over minus j is 1 over j, so it's sort of capacitive, assuming z0 is 0. And then this, in the case of the short circuit, same thing. When you look at the input of the transmission line, in the short circuit case, it's also a function of the length, periodic function of length. Notice this tangent. Tangent is a periodic function. Here, tangent is a periodic function. And this is equal to plus j times that. So the input impedance of a short circuit length of transmission line, assuming it's a lossless transmission line, it looks inductive. It's kind of interesting. Okay, so let's look at these things. So let's say we don't know. So how can we use this? How do we make this useful? So one, assume, let's say we don't know. Let's say we don't know z0 of a t line and we're trying to measure it. So we can figure out z0, figure out z0 by make the end of the line an open circuit end of line and measure input impedance. That's gonna be ZOC. And then B, we would short circuit the end of the T line. Both short circuit and open circuit, of course, are kind of like sort of easier to do than other impedance, right? Because open circuit basically means you don't put anything there, it's open. Short circuit means you have like an actual like hard short at the end of the transmission line. So other impedance is obviously more difficult to know exactly what that impedance is, but short and open circuit approximately are sort of easier to know because you can just again hard short or just open. So end of the line, short circuit the end of the line. So there with that you end up with the input impedance you short circuit, and then basically the characteristic impedance squared is the two multiplied by each other. Short circuit, and that's equal to minus j z0 over tangent of beta L times j z0 tangent of beta L, which of course these two cancel each other out. These guys sort of give each other 1 and we end up with z0 squared. All right. Okay, so now, okay, so the other thing we can do is Now let's say you have, let's look at the short circuit transmission line. So to the short circuit transmission input impedance of a short circuit transmission line. That's short circuit is plus J Z0 tangent of beta L. And notice that beta is, these are definitions, omega over the phase velocity. Phase velocity of a lossless transmission line is 1 over square root of LC. So beta is omega square root of LC. Okay. Now assume you have a very small section, assume a very small section of transmission line with end shorted. Okay, and assume that length is section, so that's, oops. And so think about a very small section of transmission line and assume that very small section has a length delta and it's short circuited at the end. And we want to look at the input of this at the end. We want to look at the input impedance. Okay. So the Z short circuit is again Z in times plus J tangent of beta L. So then if L is equal to delta is very small, then you can do this as an approximation people do geometrically. If this holds, then you can assume that tangent of beta delta, sorry, delta is approximately equal to beta delta. So at very small values of tangent, the tangent just looks like whatever you're getting the tangent of. So if you look at the tangent function, for example, it kind of looks like this, where this is sort of minus pi over 2, and this is plus pi over 2. If what this assumption is saying is right over here at very small values, the tangent just looks like a straight line. Okay, so that's what it says. And as you go further and further away, so as this value gets bigger, you then you can't make that approximation. But right over here, when the value is small, you can make that approximation, this approximation. Okay, and then if you make that approximation, Z in, so the short circuit current, so not short circuit current, short circuit impedance at delta is equal to plus J Z sub 0 beta delta. Z sub 0 is square root of L over C, so this is plus J square root of L over C beta delta. And beta is omega square root of LC. So this ends up being plus J square root of L over C omega square root of LC delta, and that's equal to plus J omega L delta. Okay, so basically what this says is that for very small lengths of transmission lines, so when the lengths of transmission lines are very small and they're short circuited at the end, that looks like a pure inductive input impedance. It's kind of interesting, and you can actually change the the impedance of the that inductor by just changing the length of the transmission line. Okay, you can get different values of inductors. In fact, this is what some designers do to get sort of pretty small inductors, pure inductors, by using transmission lines that are shorted at the end and adjusting the length to get very specific values of inductance, which is kind of cool. But the other thing it tells us is that for the input impedance of a transmission line, let's say in this case of a short circuit load, what happens is your input impedance impedance as a function of beta L. So as a function, this beta L includes both the wavelength and the length of the transmission line. Okay, so as a function of beta L, the input impedance is actually what this tells you, because this is tangent function, has this repetitive function. So it kind of looks like this. This is pi over 2. This is pi. Okay, so it goes from places where the input impedance is positive. So this is input impedance positive. So here you have pure inductive input impedance, and places where input impedance is negative. So here you have purely capacitive input impedance, and again then we'll switch over to purely inductive input impedance. So it's this, you get this periodic input impedance, which is, you know, sort of this interesting change in input impedance as the transmission line changes its length. Okay, so it's built up on that. And so let's look at what happens to the short circuit input impedance as we change beta L. So the short circuit input impedance is plus j z0 tangent of beta L at beta L is pi over 2. This short circuit input impedance is infinite. So that means, this means that a lossless T line with short circuit load looks like an open circuit at some length, at some very specific length. And that length is lambda over 4. Okay. And so this lambda over 4, so so let me say this, that so in the business they call a length, lambda over 4 length of T line, a quarter wave transformer. because by putting that length in your transmission line, you can make a open circuit look like a short circuit. So if you have a, or vice versa, but let's say you have a case where you have a short circuit and it's got a length that is lambda over 4, looking at it looks like an open circuit. And then I can further transform this by sticking another length of lambda over 4 and making this look again like a short circuit. So, and so on and so forth. So we have this sort of periodic thing where you're going between short and open circuits in a transmission line. And sort of this, again, this periodic relationship leads to this very famous Smith chart, which we'll be seeing in a couple lectures. But anyway, this periodic relationship between the input and L comes out of concept we introduced. This is the input impedance being, again, this we had this in our in a earlier, let me write in black, in an earlier lecture. So Zn is Z0 Z sub L plus J Z sub 0 tangent of beta L over Z sub 0 plus J Z sub L tangent of beta L. And at beta L is pi over 2, you end up with Z0 squared over Z sub L, the input impedance. So anyway, as you're changing L, basically you're going from 1 over Z sub L impedance to Z sub L impedance in sort of as you go in increments of lambda over 4. And this will lead into our discussion about Smith chart